Hello, welcome to this course on interactive theorem proving and programming in Lean 4. I have Lean installed on my computer, but if you do not have it on your computer, then you can go to this URL to try the examples that I am going to be presenting. So let me just demonstrate this interface to you. So I will write a proof in Lean 4 as a demonstration. So first of all, I will import mathlib, which is a library that contains many common mathematical definitions and proofs of theorems. So the theorem I want to prove is that if a and b are rational numbers such that a is less than b, then there exists a positive rational number p such that a plus b is also less than or equal to b. So once I have typed in the statement of the theorem, just follow my cursor and you can see that on the right hand side, Lean shows me the current tactic state, which is the current state of the proof. So we have the goal uh, to the right of this turnstile, and to the left of this turnstile or above it, we have the hypothesis of the theorem that a and b are rational numbers and a is less than b. So in Lean we prove theorems by changing the hypothesis set and the conclusion or the goal until they both match. So for example, I can write this command and observe that Lean has adjusted the goal to match whatever I set. So here I want to prove this theorem by substituting b minus a divided by 2 for p, which is what we have done. So notice that the existential quantification has gone away from the goal, and now the goal is a symbol and of two statements. So I can write apply and dot intro, and this splits the and in the goal into two sub goals. So I will narrow down our focus into uh, one of the goals, and I can type lin arith to solve our first goal. So basically what has happened is we want to prove b minus a divided by 2 is greater than 0, and we have the hypothesis a less than b. And when I typed lin arith, Lean figured out that since a is less than b, b minus a is positive, therefore b minus a by 2 is also positive. The proof is not over, we have one more goal. We have to prove that a plus b minus a by 2 is strictly less than b. So we can do this by applying lin arith once more. So Lean is smart enough to conclude that since a is less than b, which is a hypothesis, a plus b minus a by 2 is reduced to a plus b by 2, which is strictly less than 2b divided by 2, which is the same as b. Right? And you can see that now Lean shows there are no goals remaining, and we have finished proving this theorem. So you can continue to try the examples in this window or by going to this URL. So I will switch to my editor for further examples. So what we saw was an example of a proof stated at a high level, almost close to a pencil and paper proof. So we will eventually get there, but we will begin by learning the basics of Lean. Um, so Lean is fundamentally a functional programming language. So just like any programming language, we can define variables. So here I have defined a variable with name length. The type of the variable is nat, which is short for natural, and the value is 42. So once I have defined a variable, I can use it in expressions like so. And if I bring up the window, you can see that it prints 42 times 42, which is 1765. We can also define variables that are functions. So in Lean, function types are denoted by an arrow. So you can type an arrow in Lean by typing backslash R. So for most of the special symbols, Lean allows you to enter them using LaTeX syntax. So how do we define a function? Well, we use a binder which is called fun. So we say fun x goes to x times x. So this fun is a binder just like the for all binder or the exists binder in mathematical logic. So if you think about this expression x star x, by itself it does not have any meaning. But once you bind the free variable in this expression, which is x, by fun x, it gets a meaning. So this means this is a function that maps its input to its square. And we can now use square to compute squares of existing values. So if I evaluate square length, you can see that it again prints 42 square. So let me define one more function. It's also from naturals to naturals. So this time we want to compute the cube of a number. So I can write x times square x, and I can test this function by evaluating it on, let's say, 10, and it prints 10 cube, which is 1000. So you can define functions that accept multiple arguments using the following syntax. So let's say I want to define a function that takes two natural numbers x and y and produces x square plus y square. So this is the same as a function that takes a natural number and produces a function from natural numbers to natural numbers. So notice that the domain of this function is nat, and its codomain is the set of functions from nat to nat. So I accept a value in the domain, so x is a nat, and I have to produce a value in the codomain, which is a function, and the element in the codomain should be a function that accepts a nat, let's say y, and I have to add up the square of x and y. Notice that in Lean, quantification extends all the way to the right. That is, this whole highlighted expression is under the scope of the variable y, and this whole expression is under the scope of the binding of x. So I can use add sq as follows. So I can say add sq 5 8, and it prints 5 square plus 8 square, which is 89. So what is happening here is 5 is substituted for x in this whole expression. So add sq 5 is a function that maps y to 5 square plus y square. And when we supply this 8, y gets substituted by 8, and the resulting expression is just a natural number, which is 5 square plus 8 square. So each argument eliminates one fun binder. We can also partially apply this add sq function. So I can say foo is just add sq5, and foo is now a function that maps naturals to naturals, or something in the codomain of add sq. And we can say foo8 and it is exactly the same as add sq58. We can also define functions where the domain is the set of functions from naturals to naturals and the codomain is a natural. So in this case, we have to bind a function using fun, and we can apply this function to any natural number. So if we evaluate bar on the function square, we will get square of 10 as the answer. And if we evaluate bar on the function cube, we will get the cube of 10 as the answer. So a very popular function in mathematics is the function that composes two functions. So this function has type, its domain is a set of functions from naturals to naturals, and it takes another function from naturals to naturals in its codomain, and finally produces a function from naturals to naturals. So compose fg is the composition of functions f and g. So if we take an element from the domain f, we now have to produce a function that maps a function to a function. So this is the second function g, and finally the output should be a function that from naturals to naturals. So let's take a natural number x as input, and the output should be f of gx. We can use compose like this. So if we compose square and cube and we apply it to 10, you can see that we get 10 power 6 as the result. We can also compose square with itself and apply it to 10 to get 10 power 4. Finally, we want to define a function like factorial, which is from naturals to naturals. So this cannot be expressed using the usual arithmetic operations like square or cube. So what we can do is we can decompose n into all its cases using what is called the match statement. So we know that a natural number is either 0. If it is 0, its factorial is 1, or the natural number n is the successor of a natural number n prime, in which case its factorial is n times factorial of n prime. Observe that this definition of the factorial function very closely resembles its inductive definition. This is just because the match operator takes a value of an inductive type and splits it into the cases of the definition. So if we evaluate factorial 5, you can see that we get 120. We can take match statements even further. So let's define a function from naturals to naturals that is like the factorial but skips every other number. That is g of n should be n times n minus 2 times n minus 4 and so on. So let's take the number as input, apply match. If it is 0, then we output 1. Now you might be tempted to write, if it's the successor of a number, then you do n times g n prime minus 2. But we will not write it this way because we are applying the subtraction operation which we don't want to do, right? So you can further refine these into these cases. So if it is 0, we output 1. If it's the successor of 0, which is 1, we again output 1. So if it is not the first two cases, then it must be the successor of a number n prime, in which case we can say g of n is n times gn prime. So we can evaluate g on 5. So this should give you 5 times 3 times 1, which is 15. We can evaluate g on 4, which would give you 4 times 2 times g of 0, which is 8. So let us move on to propositions. So the first proposition that I will introduce is the true proposition. So if you look at the highlighted text, you can say that Lean is telling me that true has type prop, or prop is short for proposition. And if I check what is prop, you can see that Lean tells me that prop is a type. So I can ask Lean to check what is 1 is equal to 1, and Lean tells me that 1 is equal to 1 is a proposition, right? Just like true, right? So observe that true has type prop, 1 equal to 1 also has type prop, because both of them are propositions, and so is 1 is equal to 2, right? So the proposition is a type, and the propositions itself are types. So when you have a type, what you want to ask is what are the values of that type. So since 1 is equal to 1 is a type, I can write it here in the place of a type. And now I need a value to satisfy Lean. So for a proposition P, what are its values? Well, its values are exactly the proofs of P. So here I can write EQ dot refl1, which is reflexivity of equality. So if I scroll here, you can see at the bottom of the screen that EQ.refl is a proof of A equal to A given A. And I have given 1 for A. So this is a proof that 1 is equal to 1. Notice that I have written def here, but this is really a theorem, so I can replace def by theorem. If I try to prove 1 equal to 2, since this is a proposition that does not hold, I cannot write a proof here that will be accepted by Lean. So if I type eq.refl1, you can see at the bottom window that Lean is complaining that I gave it a proof of 1 equal to 1, but it expected to get a proof of 1 equal to 2. So I can try replacing this with a 2, and you will see a similar error that I am giving it a proof of 2 equal to 2, but it is expecting a proof of 1 equal to 2. So there is no proof I can write that will satisfy Lean because it is sound and this proposition does not hold. So I can say sorry, which will be accepted by Lean anyway with a warning. So notice that there is a yellow underline and there is a message that says that declaration uses sorry, which means it is not a real proof. So I can prove the theorem true. So recall that true is a proposition, so it can be used as a type. So what is a theorem? What is a proof that proves that true holds? So this proof is called true.intro. It is provided by Lean. And if you look at the bottom of the screen, you can see that Lean is telling me that true.intro is a proof of true. Or equivalently, true.intro is a value of type true. So let us consider the proposition true and true. This proposition also obviously holds, but if I try to prove it using true.intro, it fails because true.intro is a proof of true, but it's not a proof of true and true. So how do we construct a proof of an AND? The way we do this is by using and.intro, and if I place my cursor over and.intro, you can see that Lean complains about a type mismatch. So I can say true.intro, and notice that Lean has accepted this proof. So the reason for this can be understood by looking at the bottom of the screen. So observe that it says and.intro is a proof of A and B given a proof of A, which is called left, and a proof of B, which is called right. So to prove this proposition, we have to provide Lean a proposition of this true and a proof of this true and a proof of this true. So this true.intro proves the left hand side true, and this true.intro proves the right hand side true. And finally, the and.intro combines these two proofs to prove the and. So this is exactly the same as defining natural numbers. So let's say I want to define the natural number 3. So I know that it is the successor of the successor of the successor of 0. Observe that we are constructing larger and larger natural numbers using this inductive definition. Similarly, we can construct proofs for larger and larger propositions from proofs of its constituents. Let us look at how we can prove an OR. So true or false obviously holds, and I can prove this by writing or.inl true.intro. And if I highlight this, you can see that Lean is telling me that or.inl is a proof of A or B given that I give it a proof of A. So INL is short for introduce left. Here in the OR, it is the left hand side that holds. So I say that or.inl true.intro, that is the left hand side holds via true.intro. Similarly, I can show that false or true is also true, is also holds by using or.inr. So this is the other introducer for OR. INR is short for introduce right. So if I replace this INR with INL, notice that Lean does not accept my proof. It says that I have provided a proof of true, but it expected a proof of false because the left hand side proposition is false. So this is all for today. Let's meet again next time. Thank you.